let's get started again with the turbulent boundary layers. So to understand the nature of a turbulent boundary layer, I would like to consider a certain class of flow and then apply the equation that we have derived. Okay. So first I would like to consider, a thin boundary layer. A thin boundary layer. It could be a thin shear layer also. So what this thin boundary layer means is that we would need two length scales. So if I take the, let's say this is a wall, an infinitely long wall, then we have this boundary layer growth. So let's say this is our growth of the boundary layer. Then we are saying that we need two length scales. This is L, which is a function of x. X is the x coordinate here. Let's say I'm using xy coordinate here to make it simple. And this is the thin region that Prandtl talked about. That is the boundary layer thickness, which is a function of x. As you walk along the x direction, the boundary layer grows. So a thin boundary layer implies that you would need two length scales here to define this flow. One is L, a horizontal length scale, delta is a vertical length scale, both functions of x. So when I say consider a thin boundary layer, it means two length scales required to define the flow. Okay, so that means we have chosen L of x and delta of x in the x comma y directions respectively. Two scales. So we are introducing scales now. We are already taking a problem. So far we have done only governing equations. Now we have taken a problem and we are introducing scales to see how turbulent boundary layer looks like. Okay, two scales introduced, and we will also consider statistically stationary flow. Okay, the flow has come to a statistical stationary state. So consider statistically stationary flow. So this implies that the dou by dou t of the average term is 0. Okay, the mean is, it's a statistically stationary flow. I'm not talking about statistical stationarity that you achieve in this flow. I'm taking it as statistically stationary flow. That is, the mean is no longer changing with time in this problem. Okay, and then I would also consider statistical homogeneity in one direction. So I'm going to take a planar boundary layer. So turbulence is still 3D here, but from mean flow dynamics point of view, it will be a planar boundary layer. That means the out of plane z direction, I am taking it as homogeneous. Okay, we already studied what is statistical homogeneity. So I am considering statistically homogeneous turbulence along z direction. This implies dou by dou z of any statistical quantity is 0. Okay, so I have this condition. So with this condition, now we will look into our Rance equations. What happens to Rance equations? So consider Rand's equations now. Constant density isothermal flow, right? So rho is constant, which means it's isothermal flow. So the equation is essentially you have your dou ui bar by dou t plus uj bar dou ui bar by dou xj equal to minus 1 by rho dou p bar by dou xi plus I have the viscous term nu dou square ui bar by dou xj square minus dou by dou xj, the Reynolds stresses. Of course, I also have the continuity equation dou uj bar by dou xj equal to 0. This is my Rand's equation for an incompressible flow. Now, with the consideration I have a statistically stationary flow, this goes away because of this condition here, statistically stationary flow. So beam flow dynamics is no longer changing with time, right? So now we will expand other terms to see what it looks like. And I have also the third direction, gradients along the third direction. Gradients of the mean quantities along the third direction is 0. Okay, gradient of not the fluctuation, statistically homogeneous. So if I expand it, I would get, if I write in terms of xy coordinate I equal to 1, so I would get essentially a u momentum equation, u bar equation, which will be, I will have u bar dou u bar by dou x, v bar dou u bar by dou y. You can write in the Cartesian tensor also, since it is coming to a planar and we would not need so many, it's only a scale analysis, so I don't need a tensor so much. So I'm going back to this xy coordinate system, and then I have minus 1 by rho. So I equal to 1, so pressure gradient is applied along the x direction. So I have dou p bar by dou x, and so the third one is already 0 here, so I'm not writing it here, but okay, I can write it down. The third one, which is your w bar dou u bar by dou z, this is 0, okay, because of the statistical homogeneity along the z direction. So I have minus 1 by rho dou p bar by dou x plus, again the three components, one dou by dou x will be 0 here, so I have mu dou square u bar by dou x square plus nu dou square u bar by dou y square plus nu dou square u bar by dou z square. Again dou by dou z term is gone, and then I have the Reynolds stress terms, three Reynolds stress terms, minus dou by dou x of your, this is j is repeated, u is there, u prime is always there because I equal to 1, so u prime minus dou by dou y u prime v prime minus dou by dou z u prime w prime, u1 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 u2 u1 u3. Again dou by dou z is gone because of statistical homogeneity. So I get only a reduced form of u momentum equation here. Similarly, you can get v also equation. Let's say if I take I equal to 2, which is the v momentum equation, I'll get u bar dou v bar by dou x plus v bar dou v bar by dou y. Here also one of the term goes away, which will be equal to 8 minus 1 by rho dou p bar by dou y and then I have plus nu dou square v bar by dou x square plus nu dou square v bar by dou y square minus here minus dou by dou x of u prime v prime minus dou v prime by dou y. And the other term, dou by dou z terms are gone. So the three terms here again is going away. And of course I have the continuity equation also. So this equation here gives out to be for dou u bar by dou x plus dou v bar by dou y plus dou w bar by dou z equal to 0. Again statistical homogeneity along z. So these three equations here constitute, say this equation, let's call this 1, 2 and this 3. This is typically called shear layer equations. Okay, planar shear layer equation for a thin shear layer or a thin boundary layer. So I have the equation now. So now I am going to introduce some scales to see what is called an order of magnitude estimate. So the objective now is that in the, I will consider the u momentum only now. For the u momentum equation, I would like to see which is the largest term on the left hand side and which is the largest term on the right hand side, which is going to balance this. It need not be a largest term on the left hand side also. Basically I would like to see which are the two dominant terms that are balancing each other in a turbulent boundary layer. For that I would like to do what is called order of magnitude estimates. Some of you would have done this, order of magnitude estimates. Okay. For that I would like to choose a scale. So we do what is called order of magnitude estimates. Okay. So here I am going to choose a scale. So before that, if I mention, let's say if I say tilde here, this symbol I am going to use for what is called order of magnitude. If I am going to say this, if I set two terms left and right side of this symbol, that means they are of the same order of magnitude. If I am saying u bar tilde v bar, means u bar and v bar I am considering of the same order of magnitude, not same value, same order of magnitude. Let's say u bar is 1 meters per second, let's say u bar is like 5 meters per second, then v bar is let's say 2 meters per second. Obviously they are different but same order of magnitude. Okay, it's not 10 times smaller, 100 times smaller, but only 2 times smaller, same order of magnitude. So this means order of magnitude symbol, order of magnitude. Then I am going to consider, as I already said, I needed two scales here, a longitudinal scale and a vertical scale, L and delta. So we will use L as a generic streamwise length scale. Okay, so I am going to use L as a, so I will take this as a generic this is basically a generic streamwise length scale. You all understand what is a length scale? Velocity scale, time scale, right? I mean, we are using scales here, right, to determine whether it is should be in feet or should be in meters. So we use a particular scale to analyze. And turbulence is characterized by eddies, vortices of different length, and some can be as big as a kilometer and some can be like a micron. So we are introducing scales here, right? That is the idea of a length scale, the size of an eddy you can think of. And then we have the delta, which is also a generic lateral length scale. And then I need a velocity scale here for the two directions, for the x direction and the y direction. So I am going to choose a generic velocity scale. I will call this, let us say, US. This is my generic streamwise velocity scale. And I will have Vs as the generic lateral velocity scale. Like your UV component. Okay, these are the scales that I have chosen. And then I will have, if I say dou x, I would take this particular thing as L, or sorry, I will have used this as, when I say dou x, I am going to use L here, the scale that I am going to use for dou x, and for dou y it is delta, the two scales that I am going to use here in the equations. And for the velocities, I have, if I now look into the equation, I have dou x and dou y terms, dou by dou x, dou by dou y, that I am using two different length scales here. And I also have velocity u bar, v bar, and also changes in the velocity, dou u bar, dou v bar, and so on. So for u bar, it is us as before. So I am going to use u bar is same as, for u bar I am using us velocity scale. But then I have changes in u, right, dou u bar, dou square u bar, the second order terms changing. So here I am going to consider that this changes in u, either first order or second order terms, they are of order of magnitude different than u bar. Okay, so dou u bar, dou square u bar, I am going to consider it as at least an order of magnitude. It can be more than that. So let's say it's at least 10 times smaller, and it could be 100 times or 1000 times smaller also, but at least an order of magnitude different. So I cannot use the same scale us, I need a different scale. So for that I will use, that is the changes in u. So I am going to use for this dou u bar and dou square u bar. For both of this I am going to use a scale called delta us, not us but delta us. That means delta us is at least an order of magnitude different than us, right. So that means here u bar and the changes dou u bar or dou square u bar are of different orders of magnitude. Okay. So what else I have? I have u bar, dou u bar sorted out, left hand side is fine. I have v bar, I will come to that. I also have, so I have the lateral velocity component v bar and also its changes. So since it's a thin boundary layer, the v bar itself is tiny compared to u bar, right. The x momentum velocity is large compared to the lateral. So v bar and the changes in v bar I am going to take a same scale. So there is no like a golden rule here that I should choose this particular scale or that. You have to make an argument and choose a scale. If you don't have a thin boundary layer, right, if your v bar has significant changes, then you choose a different scale for v bar and changes in that. So for the flow that I am considering, I am making an argument that v bar and dou v bar, dou square v bar all will have same orders of magnitude. Okay, that does not mean that they have same values, right. So let's say V bar is 0.1 meters per second, dou V bar may be, let's say 0.2, or so it's the same order of magnitude. That's what we are talking about. So I would take for V bar, dou V bar, dou square V bar. For all these components, I am taking a single velocity scale called Vs. That's the lateral velocity scale that we have. So that means it's V bar is small here, right? V bar is small, and V infinity bar, if you go to the free stream, it is 0 in a thin boundary layer. The same thing applies also to if you are doing a thin shear flow, that is for a jet, wake or other flows also. If your growth of your shear layer, the growth of the jet is, as I said, it's a thin jet that you are taking. The delta is an order of magnitude smaller than L. That kind of a jet if you have, you can use the same scale. But if delta is growing, the delta there is of course the, let's say, the diameter of the jet. If that is growing very fast comparable to L, then you can use the same scale or a different scale. You choose depending on the flow. For the flow I have taken, this seems reasonable. Okay. For this, and then I have the Reynolds stress component, right? I have this U prime bar, U prime V prime bar, and other components, right? So here I am going to take the same turbulence velocity scale. I cannot use US and VS because this is the momentum, mean momentum. So turbulence velocity, I want it to be different, not use the same. But if you recall the data that I have shown to you once about the RMS data, right? I showed you a graph with U, V, W, RMS in a plain turbulent co-ed flow. There the values are different, showing anisotropy, but they are same orders of magnitude. If you recall that figure, they were like the URMS, let's say, is 0.5, then VRMS is 0.3 and WRMS is 0.2 or something. They were of the same order of magnitude but exhibiting anisotropy. So we are looking into only order of magnitude. So for that reason I am going to take for the turbulent components, dou square, dou U bar, and then I have dou V bar, and then the shear term, dou U prime V prime over bar. For all this I am taking a single turbulence velocity scale. Okay, so this is here, the small u is nothing but a generic turbulent velocity scale. Okay, so this implies that they are of the same order of magnitude. The URMS, VRMS, and this U prime we can think it of as URMS, VRMS multiplied together. So we are thinking of that kind of a quantity, right? So same order of magnitude here. That is, you have your URMS is of the same order of magnitude as VRMS. Same order of magnitude. Okay, so now I think we have all the scales ready except one, that is V bar, right, and also P bar for the pressure and the velocity. So what do I do for the V bar is essentially I use the continuity equation 1. Okay, so if I take here, okay, if I say using continuity here, using equation 1, I have dou U bar by dou X equal to minus dou V bar by dou Y. So I can simply say here that dou U bar, I have a scale delta US by L, is of the same order of magnitude as dou v bar, that is Vs, a generic velocity scale. I am just putting the scale that I have already taken here, and delta. So this means that this gives me basically Vs is nothing but I have delta Us delta by L. So delta by L indicating the boundary layer growth, right? Both are functions of x. Delta is the boundary layer thickness. So Vs I have got